You'll have seen that last time we were talking about material properties, and so I'll just, in line with just rolling through some things here, there's always some relevance in the things that we'll talk about in these little videos. That's why I want to be able to chat about them rather than answer questions about homework per se. We talked about material properties. So we talked about densities of fluids and gases, equations of state. We talked about compressibilities or moduli of those materials. We talked about viscosities, and I guess we talked about interfacial tension, water and air to be able to define those behaviors. We talked about how those behaviors change from solids to liquids to gases. In this class, we're only dealing with liquids and gases, fluid mechanics. And so we have some kind of feel for that. We talked about dimensionality and how you can only add apples to apples and should only do that. And so now we move from that to be able to talk about how we project those behaviors when they're controlled by conditions around them. And so those are pure properties. The compressibility of a gas or liquid is a property that is perhaps a function of pressure and temperature, as we found out yesterday or on Friday. But now we're interested in looking at how we can use that information to define behavior. So the first activity that we'll do is to be able to understand pressure at a point. And so to do that, we need to know not only something about the material properties, but also about the material around it. So to get the pressure that you're experiencing, which is 101 kPa, you have to know something about the column of air above us that goes up to the top of the stratosphere, is it? Where it goes to a vacuum. And that's the weight that's acting down on us. So clearly knowing something about the material around us is something that we have to be able to accommodate. And so that's relevance in the free diving. You know that pressures increase in your ears as you dive in a swimming pool. Free diving is an interesting pastime, I guess. You have to go as deep as possible, but it's always kind of an unknown because you're holding your breath and you have to make it all the way back up again. So the deeper you go with a full tank of lungs going down might not always get you to the surface. Likewise, pressures in air change from sea level to elevation. This is the Hillary step, the big step before you get onto the top of Everest. I guess some people have oxygen in a previous clip. They're not wearing oxygen masks then, but the air is thin. The classic question about how long does it take to cook on the top of Everest? Does it take longer or shorter? It takes longer because the water boils earlier, so the food gets is staying at a lower temperature as it boils in the water. So that's something that relies, as we've mentioned, on the conditions around us. And what else have we got? Just a Google picture. This is probably a useful one. I wonder if it'll come up. So you'll see these if you go by the penitentiary along by the Nittany Mall and look sometimes in the Dale Summit siding, there are railroad cars for oil from the Bakken in the central US. But you see these cars are flared. They're flared upwards at the ends. And the reason for that is if you take water in a container and you accelerate with it, it's like putting a bulldozer in the surf zone in the sea and going along. You know that you'll get kind of a bow wave. It's no different from a boat forcing its way through the water. You'll get a bow wave that's elevated. And so the idea for this is that as you start moving a tank, the acceleration, not the velocity, but the acceleration of that tank will tend to push the water to one end. It will rise because it can't get out of the end. And if you don't have this little flare, then potentially you can pop off the lid. And so the question you might ask is, what should that flare be? 1 degree, 2 degrees, 4 degrees, 45 degrees? And so what do we need to know to be able to calculate that? And finally, related to this, so we're still talking about fluid statics. And so that kind of seems like a misnomer sometimes. But statics means that we're talking about acceleration. How can you talk about acceleration in fluid statics? Well, the acceleration is applied to the container, and the fluid is static and non-circulating within that container. And so that's the same principle as the tankers. This is some water caught between the double glazing in the bus. The bus is accelerating and decelerating. When it accelerates, it comes up at the back. When it decelerates, it goes up at the front. And so it's exactly the same process. So we're talking about fluid statics. So it seems anomalous that we're discussing accelerations, but we're talking about a closed container. And of course, careful, I'm going to do that one of these days, I know, when I come down, break my ankle. When we talk about waves, of course, you think of waves as moving. Of course, they're not, right? If you look at the circulation with a wave, it's just a particle motion that is underneath the crest of the wave that's turning over, going up and then down, but it's not physically moving from 2 miles offshore to the surf zone. So I can't get, I don't know where to go. How do I get that? Well, I'm finished with that, so I don't need to worry about that now. So today we'll talk about fluid statics. That's our plan, as you can see here. And we'll talk about, I guess we won't really do a recap, because I've kind of done a recap already on what we've talked about. I guess I will look for my components. All right. And so I don't use these equations much anymore, but they're there. So the essence of what we'll talk about today is fluid pressure at a point. How do we calculate it? And of course, that's kind of important because we might want to know what fluid pressures are on the sides of structures. I guess it's important if you want to know what the pressure is on your ears, not really an engineering problem per se. And what we can define is we can define an expression which is always true, and that is the pressure change with elevation is equal to the unit weight. We've talked about this term before as density of fluid times gravity. This is unit weight or specific weight, it's called. This expression is always true, always true. But the magnitude of the pressure at a point you get depends on the fluid you're dealing with. For water, we know that the modulus is constant, and therefore the density is essentially constant, because you remember that modulus is change in pressure divided by the change in density of the initial density. And so if that is constant, that doesn't change. And so that's something that we need to define as a incompressible fluid, or sometimes referred to as a slightly compressible fluid, because E is not zero, but it's constant. But for the atmosphere, we know that E is equal to pressure, roughly, modulus. And we also know that, for instance, pressure is equal to rho RT, all in absolutes, right? And so we could rearrange that to get pressure as density as a function of pressure over RT. So it changes as a function of pressure. And so if you have a column of air with pressure at the bottom with a whole bunch of air above it versus sitting on the topmost piece of air that you have, the pressures on those two different pieces change with elevation. And so it may be that we have to accommodate that when dealing with that behavior. So that's our goal for today. I'm not sure where I want to do this. Maybe I'll do it, just follow on from here. So you'll recognize these things. So this would be what? No? Let me get rid of that. Oh, that doesn't work. Oh, it does work. Fluid pressures at a point. I guess it would be pressure at a point. So, and we'll talk about it initially at a very simple case. So the simplest case I can think of is if you want to know, for instance, what the pressure would be as you go down with depth. The easiest way to do that would be to take a bucket, which has some height to it. Let's call it Z1, and has some area. And we know that the weight is equal to the volume times rho g, which is equal to area times z times rho g. And we know that the pressure acting up, if you want, is going to be equal to the weight divided by the cross-sectional area, just by definition. So if we substitute this into here, we get area z rho g divided by area, and we end up with the pressure being equal to z rho g. I'll write z negative. I've already mentioned to you that we'll take z as positive upwards, and we'll talk about that later, but let's ignore that for the moment. So if we wanted to, for instance, we could plot on this the magnitude of, let's call this P1 and Z1. This would be P1. This would be Z1. And we know that the magnitude that we get is this. So what we could now do is we could add on to this another bucket, a differential bucket, if you like. It gives us this. And now the pressure at 2, I don't know why it's not working very well, would be equal to P1 plus Z2, I'll call it here, rho G. Just taking this term here. This would be Z2. And so this, I guess, would be Z2, this instance here. And it would give us a curve that if I get it, you know what I want to draw. So let's get it in the right location. So it'd be something that would look like this. And so the point is that as elevation goes down, we can define this as pressure is equal to density times gravity times depth, if you like. Should call it H perhaps. H might be better, but let's not do that now. And we can also write this as unit weight times Z. And so that's the way that we can define this behavior. And you know that, right? You know as you go down a swimming pool, the pressure initially at the top, we take a 0, because this is gauge pressure. And as you go down into the water, it will increase linearly. And at some stage, at 14 feet in a diving pool, it might even hurt your ears. And so that's the easiest way for us to think about it. So what we can do then is try and come up with some more general expression to deal with that. And I mention it as buckets because they're perhaps less threatening. I'm not sure my phone's on the counter, but anyway. But what we can do is we can look at a fluid that instead of being static is also, not sure why there's a delay on my pad this morning, but on the Bluetooth, an accelerating fluid. So in other words, accelerating not because the fluid is moving, but because the container, say, containing the fluid is actually moving. Not moving at constant velocity, but accelerating. And so if we do that, then we have the background that we'd need to be able to define our behavior for the system, for instance, that we looked at for those railroad cars. And so I'll practice my drawing skills of a cube, which is now a differential cube. See how good I am. Not bad, right? And a coordinate system. Coordinate system is always right-hand coordinate system for this reason, right? Right-handed. For those not seeing this, I don't know what that is. Thumb is the X, first finger is the Y, and Z is the second finger. The Z is vertical, positive, when we do it this way. And we can define some components on this. We could define an area. This will be the component dx, dy, and dz. This is no different, by the way, from this bucket. It's nothing more than that. And we can define at the bottom of this bucket a pressure which we'll call P. Happens to be in the x direction. I'm not sure we want to label it as x because the pressures are the same in all directions. The pressure at the top will be equal to P plus, some change in pressure dP. We'll also apply to this an acceleration. We'll do it in the z direction right now, but we could obviously apply accelerations in all directions. And it will have a fluid in there which is of some density rho, which we know. What else do we have to have? And as a result of this, whoops, I didn't want to do that. Touching the wrong machine. It will have a weight attached to it, which is the same as the weight in our bucket. And so the other thing that we could do is that we could add, yes, go ahead.
The acceleration in the z direction, is it just supposed to be pointing up or?
Up. The acceleration in the z direction is in the z direction. Everything is positive in the positive z direction. Z is upwards in our right-hand coordinate system that we choose. And we'll choose that as a standard for our system.
The arrow kind of goes to the right of it and then goes up.
It means that it's attached to the thing dragging it up, is what that means. So, yeah. And so we can take Newton's first law. Underlined because they're vectors. There are forces in x, y, and z we can resolve. There are accelerations in x, y, and z. Forces are positive in the coordinate directions. Accelerations are positive in the positive direction of the coordinates. And so we can define this. These would be three separate equations. Fx equals mass times acceleration x. Fy equals mass times acceleration y, etc. If we just take the z component, then it would be Fz is equal to mass times acceleration in the z direction. So let's attempt to write things out in that format. Oh, I didn't want to do that. See if I can fit it in. So let's take resolutions of this. So what are the forces acting upwards? We have pressure times area acting upwards. We have minus pressure plus dP dz times dz times area. So we have acting downwards minus, I'm going to go down here, minus rho g v. This term here is equal to W, right? Rho g times the volume of this. So volume would be equal to area times dz in this particular case, right? And that, we could subtract from that mass times acceleration. So mass would be volume times density times acceleration in the z direction equals 0. So I'm just changing this to equal force minus mass times acceleration equals 0. So we can choose to get rid of some of these components. So clearly pressure and pressure cancel. We're left with this term. And so if you write those out in longhand, we end up with change in pressure with elevation times dz times A. That's this term here. This term here is minus rho g. What is V going to be? V is going to be area times dz. Could leave it as V, I suppose. Minus volume times density times acceleration z equals 0. So one reason for writing it in that way is that we can still divide this up, and I can write this as F minus MA equals 0. So we haven't deviated from that. And if we simplify it just by dividing through by volume, so actually dividing this time by volume, dividing by volume, and dividing by volume, oops, we should end up with dP dz minus rho g minus rho az equals 0. So that's basically taking Newton's law, throwing some things in it in buckets. Happens to be a differential bucket, but it's no different from what we did up here, but we added an acceleration to it. So the acceleration would be what I drew as before as a sub z. And for the z component, we end up with that equation. If we do that same thing for y, you can see we'd resolve for y, we'd put a pressure on here. I'm not going to do it, but you'd see it. It gets very boring. This would be a pressure plus dP. This would be a pressure on the other side, just the same as we did top and bottom in this. But if we did that and resolve things the same way, the only thing we don't have operating in the horizontal direction is the weight, because the weight is orthogonal to it hanging downwards. And so you'd imagine that the expression you get, if we now include an acceleration, which I'll try and draw unambiguously by not using an arrow that bends at all, this would be an arrow, sorry, this would be x. So let's go x. I just want to do it in z, y, some order. So if we resolve behavior in the x, then we'd get this expression. It would just be dP dx minus 0 minus rho acceleration in the z direction equals 0. And if we repeat it in the y direction, they should be partials actually, but don't worry about it. It's not important for us. Perhaps that's the least of our problems right now. So these, importantly, are the basic relationships that will govern the behavior of static fluids. Looks kind of complicated, but they're important because we can simplify them and we can get kind of degenerate relationships out of them which are useful to us. And so the degenerate relationships would be if the accelerations are equal to 0, so it's not accelerating, so it really is a static fluid, not one that is going through an acceleration. And then all these terms on the right-hand side would drop out. And so if that were the case, we'd end up with an expression which was dP dz equals minus unit weight. This term here. So if you take these as 0, then all of these terms will drop out. And we'll also end up with change in pressure in the x direction equals change in pressure in the y direction equals 0. These should all be partials. It doesn't matter. It's not important for us to worry about that now. And so this is the expression we started off with today that we said is always true for a fluid, irrespective of whether it's a gas or a liquid, that we can then use. This is the material constant. This is the change in pressure around a point. And we have to integrate this to be able to evaluate the behavior in a column. That's what we're going to have to do. The negative sign is because of our sign convention, that z is positive upwards. So that's kind of important. So that's fine. The pressure at a point will also be, we haven't discriminated between or distinguished between pressures in x, y, and z. They're all the same. It's just pressure. Single magnitude. It's a scalar value, not a vectoral quantity. And we've already assumed that we know this. This says that if you're in a swimming pool and you're sitting on the bottom, or as you move horizontally in the x or the y direction, the pressure doesn't change. The pressure doesn't change because you're the same depth below the water, z, as you move from one to the other. But it's more involved than that. We've already used it once in our class already. So last time we looked at the expression for a capillary that's present within a fluid. It looks like this. And what we said is that we can cut this off at the bottom and just use it as a simply supported structure with just air pressure acting on here. But clearly it's water or fluid, whatever it is. The reason we can do that is that we're going from this point here. This is the x direction. This is the z direction. And we're going to another point, which is not changing in elevation. There's no change in pressure as we go from here. So the pressure at this point here must be atmospheric. So it's the same as if we can cut off the bottom and we just have the water sitting there. And so we've used that expression already to be able to describe our behavior. So what do we want to be able to do with that? Well, now we can use it to say something about the behavior in a column. And so now we go back to our idea of these two fluids. So let's talk about incompressible. And so for that would be a liquid. So it could be water or gasoline for that matter, any liquid, something that exists in that form. And what we'd like to be able to do is the same evaluation as we had before. This is z, but now this is negative z, right? Because this is positive z. This is pressure. And we think it looks a bit like this, right? That pressure is equal to rho g, let's call it h so we don't confuse it. So this is the depth below here, which is h, which is probably how you're used to thinking of it. And of course we can evaluate that behavior. So first of all, actually let's look at what we physically mean by this. What does this physically mean? Well, this is the change in pressure with elevation is equal, we could also write this as equal to minus unit weight over 1. So we could also do this to define this as these two behaviors. So this is dz minus dz because we're going downwards. This is dp. So we could also write this as being equivalent to pressure. So this would be unit weight and this would be 1. That's physically all that expression means. It's saying that the gradient of pressure as you go down is invariant. It's a constant. It changes with the unit weight. And it matters what the material around it does, whether it's compressible or incompressible, as to how it will work out. And so for an incompressible fluid, we've made the point that this is always the case. So we could write dp dz equals minus gamma. We could split that up as dp equals minus unit weight times dz. We could integrate each of these between P1 and P2, Z1 and Z2, that's all we're doing. So this would be, P, right? P1, P2, Z1, Z2, and you know what that looks like. You end up with P1 minus P2 equals minus unit weight it'd be the other way around, right? Z2 minus Z1. I guess you can do it either way. Z2 minus Z1. Z2 minus Z1, in our particular case, we could think of as being equal to H. This is a bracket, not divided by. And so this says that P2 is equal to P1. Okay. Z2 minus Z1 is positive. This is P1. Why is that working out that way? P2 is equal to P1. Z2, Z2 is negative. Yeah, okay. Z2 is negative, right? So this is, you get rid of that for this, and this is equal to unit weight and H, right? Z1 is equal to 0, Z2 is equal to minus 10 meters, right? Because it's negative going downwards, and therefore this is the expression. So for an incompressible fluid, then the unit weight is constant. It's shown that it's constant because this is a straight line, not a bending line. And therefore we can always get the pressure as a function of depth. And so we end up with that magnitude coming from that. If we look at a compressible fluid, by definition, that would be a gas. Could be air, could be any gas you want to choose. So we go back to realize the fact that this relationship, as we said, is always true. It may well be that it's not linear, but it's always true. And so we know that for compressible fluid, the rate of change of pressure with elevation is equal to minus unit weight. Whoops. Rho g. We also know that pressure is equal to density times universal gas constant times T. In absolute pressures, I won't confuse it by writing the A's in. So we could rearrange that as density being equal to pressure over RT. We could allow ourselves to put that in there. So the rate of change of pressure with elevation is equal to, not now constant, but pressure divided by RT multiplied by gravity. So that's the relationship now we have to work with. And we can do exactly the same as we did before. We can split this partial differential into two parts. And if we do that, we end up with dP. We'll take this pressure over the left-hand side, and that is going to be equal to dz times g over RT. It's a negative sign in there somewhere. We're going to integrate both sides again between, what did we do? We did P1 to P2. Or backwards, it doesn't really matter. And then we can find out exactly what these components are. So this is equal to log P, this integral. So log P evaluated between those two limits, which are P2 and P1. And that's equal to, just going to be a linear component. It's going to be Z evaluated between Z1 and Z2, and G over RT. Should be a minus sign in there, I guess, for this. And if we work those out, it's going to be, this term here is P2 over P1. Is equal to Z2 minus Z1 G over RT. And if you know that e to the log x is equal to x, we can exponentiate both sides, and we end up with P2 over P1 is equal to e to the minus G over RT times Z2 minus Z1. Bit complicated, more complicated, but that's what this is all exponential term here. And so for compressible fluid, the behavior that you get is this, and I guess you could write it, if you wanted to, as P2 is equal to P1 exponential, all in brackets, of minus G over RT, Z2 minus Z1. So a little different. And so the question is, what does that quite look like? And I suppose it's probably easy to draw a little figure that represents that. And the figure would be a bit like we had before. And so this is pressure. This is elevation. This is positive Z here. This is minus Z as you're going down. Let's say this is the C that we're going through. And I guess, we know already that the pressure as you go down in depth is going to look something like this. If this is H, then this is P is equal to rho G H. Right? This is linear. This is the density of water, I guess, if we're thinking of this as being a liquid. This would be gauge pressure, if I'm spelling that right. I think I'm not. So this would be 0, if that's 0 gauge. And that's what we're feeling here. But of course, this is actually equivalent to 101 kPa absolute. So what we're thinking of as, this is an arrow, not a line. So what we're thinking of as 0 pressure, because we're used to it, is actually an absolute pressure of 101. And so in terms of gauge pressure, I guess we'd want to have, I need to do a different color line here. We'd want a barrier here, which is an absolute pressure. This is 0 absolute. This is 101 absolute. And the pressure of the air above us, I'll do it in a different color, is going to look something like this. I won't be able to draw this very well, but it will look like this. The curve that we have here looks something like this. It'll asymptote to 0 pressure absolute as you go up to infinity into space. It will build non-linearly as you go down here, because the density of the air, which is at very low pressure, will be very small here. The density of the air at very high pressure will be much higher here. And so if you look at the gradients, if you look at the slopes of these portions, right? We said already that the slope of this line happened to be linear, is equivalent to 1 unit height, and this is the unit weight. So at great depths, this will be 1 over unit weight. And at great elevations, it will equal, it'll be almost a straight line, right? It'll be something like this. It's exaggerating a little bit, but this would be 1, and this would be the unit weight. And so you can rationalize, right? That at very high elevations, the unit weight of this fluid, a gas in this particular case, is very steep. The other thing that we know from last time is that if this is, I just threw out the number last time, if this is air, then the density, it's about 1.25, but it's about close enough to 1 kilogram per meter cubed. And this is the density of water. You certainly know what that is. So these are a factor of 3 orders of magnitude different, 1,000 times different. So this would be quite shallow. In other words, you go a small depth down and you have a big rise in pressure. This would be much steeper in that you go up and there's a very small change in pressure as you go up here. So if you plotted these curves, it would look just like that. I actually did plot them, and so I'll look for that now. Let me get this. Hopefully that makes sense to everybody. I don't know if you've used Equatio. You get access to it from Penn State. Is that big enough to see on the right-hand side? So these are exactly those two expressions. I don't think I can make it bigger by making it bigger on my screen. Does it get bigger on there? Oh, it does. Yeah, okay, that's fine. So you see on the left-hand side, or maybe I can move it around just by moving this, I think. Yeah, okay. So you see two expressions. Unfortunately, I don't know how to they should come out automatically as different colors, but they don't. I can turn one off. Why don't I turn this one? You see is the pressure in absolute pressure for the liquid. So the pressure in absolute pressure is pressure at sea level, 101 kilopascals, minus 9.8 acceleration due to gravity, density of water, times the depth, y. It needs to use y instead of z. And so in this case also, y positive is z positive upwards. If I turn off the other one, you basically see a horizontal line. It doesn't exist on the left side of this axis because the axis at y equals 0 is sea level. And so the only part that's relevant is going to be the part to the right of this, because as we go up above sea level, we're in air, so this one doesn't apply. But you see it's very flat, as you expect. The other expression is exactly the expression for the pressure change in air. And so the pressure absolute, which is x, is atmospheric pressure, what we called P1 before, atmospheric pressure at sea level, absolute, exponential, the elevation, acceleration due to gravity, the ideal gas constant, 287, and the temperature, 20 degrees centigrade. Of course, it doesn't stay 20 degrees centigrade as you go higher up. And 20 degrees centigrade in Kelvin is 273 plus 20. And you see that's exactly the expression you have here. And so it hits the axis at 101 kilopascals, 101,000 pascals. And it goes up just as I drew, much better than I drew. It goes up at a shallow line that gets steeper and steeper and steeper. Shallow means as you go up a unit height, it means it's a big magnitude of unit weight. And as you go higher up on this part, a unit height is a smaller amount of unit weight. And that's the behavior. And so you can see, if you want to get some relative numbers for this, we talked about the Hillary step going up Everest. So Everest is something like 29,000 meters tall. So close to 29,000 feet tall. So close to 30,000 feet, which is about 33,000 feet would be about 10,000 meters. And so 10,000 meters on this would be halfway up here. And so you can see that by the time you go up to 10,000 meters in elevation, the pressure goes down from 100 kPa to something like 30 kPa. And so if you do our previous calculation, it's useful to do this. What do I want to do now? I guess I want to get it to normal size. If you remember our previous calculation, okay, I need to do something with this. It turns out that if you did our previous calculation for Everest, if you took this as being Everest, I guess I can do it now rather than then. So if we do the calculation for Everest, if I draw my little potted diagram of Everest going up, and you end up from sea level to 10,000 meters, which is z. if you do the calculation, right? So this is what we've called, we used it, if you do it as an incompressible fluid, it turns out that then the pressure at sea level would be equal to rho g h. If we do that for this, this is 1 kilogram meter cubed. G is 10 meters per second squared. And this height is 10 to the 3. And if you work that out, it comes out to something like, 10 to the 4, isn't it? It's 10,000 meters, not 1,000 meters. So this turns out to be 10 to the 5 pascals. So obviously it's an incompressible fluid, and we've treated it the wrong way. But it's saying that as you go up from sea level at 10 to the 5 pascals, which where we are now, at the height of this column, because of the unit weight, if you treat it as an incompressible fluid, which is wrong, then this would be zero pressure is absolute. It's not true. We just found out that it's roughly, 30 kPa or so. So it would be incorrect to do that, but it comes out with kind of the right order of magnitude solution. But we have to be careful in terms of calculating pressures depending on the fluids that we're dealing with. And that's pretty much it. Yes?
In the previous page, PW equals the 5 kilograms per divided by weights, right?
Say what?
It says PW, that formula is that magnitude.
This one?
kg, yes.
This is rho W.
That's
This is 1,000 kilograms per cubic meter.
the W is weight,
Water.
right? Water.
Water, yeah. Okay. Any questions? Any other questions, I guess? Yeah.
Go back to your fluid stacks with the box.
The buckets? Or the differential cube or the buckets?
Yeah, this box right here. And right below, like in the red on the right hand side, you have a negative.
This?
Yes, like negative dp over dc times.
No, that's the problem between P's and rho's. This is acceleration, this is mass, which is the volume of the fluid times its density. You agree?
Yeah.
Yeah. It's negative because we changed F equals ma to be this whole expression to equal 0 on the right hand side. And the acceleration is the acceleration that we're applying, pushing it up.
Okay, so when you switch to the blue ink,
Yep.
where does the W go?
What W? Oh, this one?
Yeah.
This term here is this term here. This term here should be this term here. And this complete term here, which really reduces just to this, is this term here.
That's negative?
Yes. Thank you. That's right. You should have surmised that. Yeah, you should have shouted. Yeah, that's negative.